First, I started with the two denoising method as a bilateral and NLM denoising. Both bilateral and non-local mean methods are based on the assumption that the image content is likely to repeat itself in the within the same neighborhood, and the formula that describing the both non-element and bilateral is something like that. This one is the denoising. This one is the denoising formula that the x is the denoise pixel, and the y is our input image, and the w is the the weight for the I and j is the weight. It means that for each of the I and j in the neighborhood, this one is the neighborhood of the KL. If, for example, if this one is our image and the KL is here, and we have the neighborhood around this pixel. For each I and j in this neighborhood, we try to find the W, KL, IJ, and also we use the pixel of the IJ, and after that just put it in the formula and find the x as a denoised image. The difference between the bilateral and the non-local mean method is just in the ways, defining the weight. For the bilateral, we just try to do something like that. For the weight, bilateral, and for the NLM, is similar to the bilateral base, but instead of working on just for the pixel, we extract the patch, and after that finding the norm, the norm 2 of this patch. If negative operator. And the function of f is the non-increasing function, something like the Gaussian function. And you can see that if the extractor patch here, if this one just extracted 1 pixel, these two exactly are same.
So when was the bilateral rate introduced?
What do you mean?
Yeah, when and who introduced that?
Yeah, the NLM is with the 2005 and the bilateral is for the 1998. Yes. With the Tomasi and Lucci.
It's also in the context of superresolution. The 98 paper is about superresolution.
No, these two, the original is for the denoising.
Oh, okay.
And both of them is for this, for something the formula and just right here, this one is just for the single denoising, not for the video denoising, just for the single image denoising. Okay.
But for the 98 paper,
Yes.
how did they define the F? They mentioned that was
The F is exactly the same for the both of them.
But you mentioned like for advanced paper, basically the picked F is just a constant.
Oh no,
There's the superresolution.
yes, the F could be the Gaussian function or the content.
Yep.
Constant.
What did they recommend in the 98
They didn't. Oh,
I guess they probably recommend something like when they first pulled it out.
in this paper, the LL paper, they said that exactly the Gaussian function. I didn't check but I should check it also. Yeah, I will check it.
Okay.
But they didn't say. But they said that the F for both of them are same. But the difference is just for this side. This one is a pixel, that one is for the patch. Now I want to have I want to write the penalty function, but in this penalty function I would like to have the proximity between the reconstructed image and also the input image, and also I want to have each patch in the resulting image, I mean the denoised image, each patch just to resemble the patches in its neighborhood. So for this design, I would have something like that. This one should be the map function. The function is the map, and so this part is same as something I said that I would like to have in my reconstructed image, the proximity between my reconstructed image and also my input image. And also, I would like to have, in the next, I will show you why I put the one force here. Like for each KL in the now this one is mean that omega is mean that all of the pixels in my image, and in the neighborhood of the K and L. Because I want each patch in the resulting image to resemble the other patches in this neighborhood, and also because the is not exactly the fit for this finding these patches. So I put the weight here for these two pixels, IJ and K and L. Sorry, this is Q, K and L. And here I have the KL is for the X, so the XN pattern of the X, and also of the Y. So something is X, because I want to have this type for just X. And one thing that this R as the patch extractor is not the same as the size. I mean, the size of this kinds of extracted patch is not the same as the patch extractor in the double. If you remember, I put the R hat for the double. What this one is R. So I mentioned here. And yes, that's it. So now I should try to minimize this one with respect of the X. So instead of this one. X. So this one is the plus. What I didn't put here, but those are the same. Also, I have this one. And the judgment of the RKL is mean that this one is mean that we want to extract the patch around the pixel of the KL. But this one means that we have the patch and we want to just assign this patch to the pixel of the KL. So it means that we have for this one, for example, if we have the R of the KL of the X, it means that I have the zero, the image of the size of the X, but it's a zero pad, and when I have the patch, I put the patch exactly in the same position of the X, the location of the X here.
What's the meaning of RKN?
RKL is the RKL is mean that this one extract the patch around the XL, X and L.
It's the center of the...
Yes, the center of the XL from the X.
And what's R transpose?
The transpose, something I said that this one assign the patch to, exactly is the difference, these are the inverse. this one is the find the patch, or find the patch from the, for example, this one is the KL, this to here for the R, but this one exactly have the patch assigned to the KL.
So R is unitary matrix.
This one, this is the yes, matrix.
Unitary matrix.
Unitary?
Yes. Also no.
Oh yes. Okay. And also we know that if I and J is in the neighborhood of the K and L, this means that the K and L is in the neighborhood of the I and J. Yes? For example, if this one has our image and this one is our K and L, so for example, if this one is the I and J, now I and J is in the neighborhood of the K and L, if this one is the neighborhood of the K and L. So if we have the neighborhood around the I and J, something like that. So now we have the K and L exactly is in the neighborhood of I and J. If this one can see the I and J, IG can see the KL. And also another thing, it has the W of the KL I and J is equal to W of the I and J and KL. Okay. So from these two, I can say that this one and this one are same. Because just the I and just the index just changed. Just the name of the I and J changed. And also I can say that these two are same. Because just the KL is here and this one. So now this one is equal to lambda x y plus if this one is 2. Now you can see that why I put them on first here. Because I don't have it here. Okay. It has the strategy that they call it as a yes. Yeah, now I wanna solve this one. But I'm trying to use the one iterative algorithm for finding the ifs from here. And it has the name of the name of algorithm is the maybe I can just write it down. Okay, so I want to find that I want to solve this one with the one iterative algorithm. That my the xn is the current my current image, and the x of n minus 1 is the previous x. So these two xn from here and after lambda I plus extract the path from the KL, and this one just backs the path exactly to the KL, and so this definition is the positive yes, the positive symmetry, and also this one is mean that this means that we have the matrix, and just put exactly all of it in this diagram. So, and also this part is mean that we have all of the lambda here. This one is a diagram also. So I can have the xn from here lambda I plus oh, yeah, I think I forgot the y, yes, exactly. I forgot y here. So now it's easy because I have the xn for finding the x, the current x. This one just depends on the x and minus 1, and also I have the input of the x also. And but in this paper they just put was one iteration, and it means that for the x0 we assume that the x0 is equal to y, and the x1 is our resulting is equal to x1. So and another thing that we have, now we are assuming is that we are assuming that the Rij just extract one single pixel. So Rij of the and okay, so from here I had something like that. This is one and also I assume that the Rij is just exactly one pixel. So Rij of the y is equal to the y of the Ij. It's just the one pixel of the y. So I can write this one as a all of them as a W also. W also. Because this doesn't depend on the Rij.
You replace n minus 1 with
Yeah.
y.
Yes, exactly. I agree with that. So from here, I can get that for defining each of the pixel of the x, I can do exactly same as the first formula that I wrote for the denoising. So for each of the k and l, I can have this formula, the first one is just to have the lambda y. The first method is as an alternative path for the denoising formula is the basic. This one is the as a that the x0 is equal to y, and you will try to find the x1 as a x1. So we don't. If you remember, I had the lambda over 2 of the. For this formula, I don't need this one. I just want my not function is just exactly is similar to this. Is this one? As so again, I try to minimize this one. So this one is equal to 0. So exactly the same as I did before. I have for the x so this one means from this one I can exactly have the R and J. I put this one, as it just exactly one pixel, this one is equal to R and J.
I don't understand why the second one is called Bayesian.
Why the
Why it's called Bayesian? I mean,
what is the Bayesian?
yeah.
For the Bayesian, we just changed the x. It was x before. Just put it the y here, and we don't need the rest of that in the map with the map and function. In the Bayesian, we just mentioned that okay, because we know that x0 is equal to y, and we want to each patch that we are finding in the neighborhood of the KL just simply it just looks like the patch around the XL, the pixel of XL in the X, and also we add the W. So here we don't have any the lambda I or lambda y here.
And the W is the same.
Yeah, W, but all of them is same, and the W also is the. We know that before the finding the Z X here, we know exactly what's the W, and I mean that we found W before, and after that, the finding the X, just put the W here. Exactly same as time here.
What do you call the first approach?
The finished one, the relational.
Yeah, the first one, you present, like what
Oh.
you call that? With the lambda.
They just say as a, or this one just say as a penalty function. They started the penalty function.
What?
The penalty function. They
What
that
function
is,
again?
yes, something as a penalty function.
I can't hear the term.
The penalty function.
Oh, penalty function?
Yes. Here we want to just say that for the denoising division is similar to that one, but we don't have these terms here. And now I want to add the time, because here we have just the image denoising, and we are working exactly just the one image. And if we want to add the time,
And the size of input and output are the same.
the same as the RME, which one? Oh yes, because the denoising is not a super resolution. For the all of them is same. And for the adding the time as a temporal here, our current function is something like that. And we have the T also. T is 1, T2. And the BT is the number of frames. This one is the and in the W also we have the KL, IJ, and T. And I will explain why T. And also here is the same as before. KL is well, but this one is a Y T. It's not a Y. Because we are working on the sequence, and for example, if we have the one, and this T is the number of the frames, and also why we are putting the W here. Our W is not the same as the W. It's the same as the W that we had for the NLM and bilateral, but the function, the input of the function is not same. And if you remember, in the function we had the I minus a, and now we have the T minus T0, or for example, if we are working on we are denoising our first frame, so this one is for example, if we have the 0, we started with 0, this one is the first frame, so this one should put here. And exactly this function is the non-increasing, the same as before. Okay. The minimizing, this one is the same as something that we did before. So now I just write the last formula for finding the x. The denoising of the first frame, for example, for using the one sequence. Here is the YT.
it's IJ or KL.
This one is a KL. This one is for IJ. Example if. This one is our Y. And this one is our X that we are trying to denoise. The KL is in our resulting image. But the IJ is in our input images. And here is the same, but we have the T also here. INJ is the neighborhood of the KL. And also we are the same. Okay. Now this one is the formula for the video denoising. And if now I want to change this one to the super resolution.
Excuse me, before going to the super resolution, in the first method, what was the result of xij
This one.
for the first method?
This one was the denoising, but it was for the image, just for the one single image.
Yes,
single denoising.
yeah, but I think you explained two different methods.
Oh, this one, sorry, this one KL again. Sorry. I
You
just talked
explain.
about two of them. One of them was the single, and another was the video.
I think you explained two methods for the single image.
Yes.
Okay, what was the first one, the output of the first one?
The output first one, if you remember, has the lambda and the I here,
Okay,
and then the Y.
yes.
Okay. Now I want to change this one to the super resolution method. For the video denoising, we don't have any resolution, so the size of the reconstructed image, denoised image, and the input image are same. But in the super resolution, they are not same. So, and also we have the blur input images. Here again, let's see. This one is not here. Sorry. So I should put as a D and H. This one is a decimation operator, and this one is a blurring. This one is for blurring. Which means that if this one is our high resolution image, this one apply, if H applied on X, this one is a blurry high resolution, and if this one applied to this part, so I have the images that degraded by this one has a blurry, and also it has the small one as a low resolution. And also because I have the deblur, I have the blurring here, I should add another. And this part, this term is for the blurring of the X. It's all X. Here, I wanna change the D for the as a DP, and also I wanna bring the RKL from here to here and just put this one to here, and that changes this one as a DP. But it has the one problem, because the RKL, as we said, this one it was same as this one. The patch that they are extracting. The patch of this one, if this one is a Q by Q, now this one is a Q by Q. But if I put this one here is not true because the resolution the resolution of the resolution of the x and the yt, they are not same. I mean that the KL, the pixel of the KL is not the same as resolution that the XL is in that image. For example, if this one is my YT and the RIJ is this one, if this one is my RIJ and this one is my X as a high resolution, and the size of the, if S, for example, S is my resolution factor. This one is K and L, so my RKL cannot be the same as this one. Now I have the new RKL. So I just defined the two patch extractor as a RKL. Maybe I can just say as a for the high resolution and also for the IJ, this one is it for the IJ resolution, low resolution. And another thing is that because the I and J now is not in the same resolution that the KL is in the depth resolution, so this one doesn't work. So I should have another name. I should define another neighborhood. So I define the I and J in the N level. Let's call that N. That's why it's mean that the SI and SJ is in this neighborhood of the KL, our previous neighborhood. And another thing is here that if this one extract the P, this one extract the Q by Q, this one extract P by P. The P is equal to this. And for example, if my Q is equal to 3, so I have, and my S is equal to, for example, equal to 2, so example, if I have this way my Q and Q. The patch is the exact patch in the low resolution. If this one is the QY group, now it's the QY tree. In the high resolution, I mean, you should just extract the 5 by 5. This one is method. I mean that the superresolution is just when we run it, the superresolution method just wants run the superresolution. But some of the superresolution method, they have the two parts. They have the debellering and they have the denoising part. This method is the same as that one that we have the two parts. Here as the debellering part, and this one, as we solved it before, as a denoising part. And another thing is that we can have the hx as a z if we want to solve this one. We can have the hx as a z. So if we want to write it again, maybe just this one is a z. So I can write it something like that for solving these two terms in the one product function. I can write it something like that. And also for finding the z, because here we're just trying to finding the z. And for finding the x from the z, we have just call this one is a exception. Just put this one for the blaring part. I want to find the x from the z. So for this part, we just use the one debellering method. But for this part, we are using our denoising formula that I explained it before. So this one is just for we can just use the one debellering method. Because as you see here, the z is the blurry high resolution image. We are finding the after denoising of the z, after denoising of the z, we have the z as a blurry high resolution image. For finding the x, as a high resolution image, we should apply the one debellering method on the z and finding the x. Again, we just the derivative of the z. Call this one as a superresolution. see here is the same as the example that before we had for this one. And for the, now I want to just simplify this method as Rij just for one pixel. So R just extract the S by S, the patch of the S by S of the around the KL. And finally, I can write the C of the KL and here you can find for the each of the KL in the Z for the very high resolution. Maybe just thought that this one is same as something that we had for the video dynamizing. First of all, this one is not same because for the video dynamizing we had just N of the KL, but here we have the NL. This one shows that our resolution factor that we have. This one shows that our Y is not the same size of the Z. Yes, and also for finding the W, because the KL is not the KL is from the Z. And also, the KL is from the Z, but that one, the KL is from the X. So we have two differences here. One of them is our neighborhood, and also another thing is Z in the value of the KL.
They cannot.
Yes. Yes.
Oh.
No, I'm not. Yeah, this one is the last equation for finding the biliary function, and after that, just apply the deeper for finding this X. Yes. If you have any question, I can ask you.